Hi. Okay, in this lesson, we're going to learn how to solve homogeneous equations. And the first thought that might pop in your head is, wait a minute, we talked about homogeneous as a part of a linear equation. Well, unfortunately, in math, this is one of those words, homogeneous, that is, that gets kind of abused. It's used in several different contexts. So the term homogeneous that we're going to talk about today means something different than it did when we introduced the concept of homogeneous and linear equations the first time. So let's get to looking at what we are going to mean by homogeneous in this context and how to solve such equations. So remember, we had our general first order equation could be written as dy dx is f of x and y, okay? Well, we're going to say that this equation, an equation of this form, is homogeneous in this sense if it, by it I mean f, the function f up here, is really only dependent on the ratio of y over x, or equivalently, you could say of x over y, and not really on x and y independently. Excuse me. So let's look at an example. Suppose we look at the equation dy dx is y squared plus 2xy over x squared. So the first thing you notice is that you could rewrite that as x squared, y squared over x squared plus 2xy over x squared. And now you can simplify that a bit to write it as y over x quantity squared plus 2 times y over x. So this function, this right-hand side, really only depends on the ratio of y over x, not on x and y each independently. Okay. So that's a homogeneous equation in this sense. All right, let's look at another example. This one's not quite so obvious. Suppose I take dy dx as ln x minus ln y plus x plus y over x minus y. So at first glance, you look at that and you say, wow, I don't think that looks like it's going to be homogeneous. You have a subtraction of two things. But let's not be so quick, because by properties of logarithms, when you subtract one log from another, that means you've divided the numbers. So by the properties of logarithms, those two terms can, in the first two terms can be combined to be ln of x divided by y. And then in the last term, I'm going to multiply by 1 over y. So I'll get x over y for this x, y over y, which is 1, x over y, and then minus y over y. Okay, and so if you notice, that really only depends on the ratio of x over y, even though it wasn't obvious at first. So that's a homogeneous equation. Let's look at one last example. Let's look at the equation dy dx is y cubed plus 2xy over x squared. And now when you go to rewrite this, you get y cubed over x squared plus y over x. So you see, you're never going to get this to depend only on the ratio of x over y or y over x, because here you have a y cubed and here you have an x squared. So it can never only depend on y over x, because the best you could do would be, say, to write this as y times y over x quantity squared, but that's still, you have that extra factor of y. So this is an inhomogeneous equation. And so the method that we're going to learn next would not work on this last equation, but it would do just fine on these first two. Okay. Okay, so how do you solve homogeneous equations? Remember, everything we do in, well, most everything we do in this first couple of chapters is learning how to use the right tricks. So what we want to do is get a big bag of tricks, and we've already learned a few, and here's another one. When you have an equation that's homogeneous in this sense of homogeneity, set V to be the ratio of y over x. Equivalently, you could do it for x over y, but I'm just going to do it always as y over x. So we have one method and we're consistent the whole time. Okay. Now, when you do that, when you make that trick, now you could just as well say then y is equal to x times v. Okay. So since our original equation, dy dx is f of x and y, only depends, that little f only depends on the ratio of y over x, we can just as well write that equation as dy dx is some function of y over x. Now it's going to look different, so I called it a capital F. It's going to look different than that little f we had before. And then when you do that, now we already know that this is our trick. And now by the chain rule, the derivative of y with respect to x is x dv dx plus v times the derivative of x, which is just 1. So I can rewrite this left-hand side to be only in terms of v and our independent variable x. Okay, and so we get our equation in this form: x dv dx plus v equals capital F of v. Okay, all right. So now the question is, can we solve this? Well, let's play around with that a little bit. Okay, so at the bottom line, we had x dv dx, x dv dx plus v equals f of v. Okay. All right, so that says, rewriting that a little bit, it says x dv dx is f of v minus v. Okay, and so rewriting this a little bit more, it says dv over f of v minus v is equal to 1 over x times dx, just using some algebra to rewrite that. And now notice something. On the left-hand side, this is function of v only. And on the right-hand side, this is a function of x only. So it's separated. It's separable. So we can solve that using our separation of variables trick. So in principle, we can solve this by integrating on the left and integrating on the right. Now that's of course provided we get something we can integrate here. Okay. All right, so we just have to see if we get something we can integrate, we work it out, solve for v. If you can, and then v is equal to y over x. So you could get y by taking x times v. And then that would give you your solution. All right. So now let's start with that first example we wrote down and see if we can work it out and see what we get. Okay. So our first example of a homogeneous equation we wrote down was dy dx was y squared plus 2xy over x squared, which we said we could write as y over x squared plus 2 times y over x. And so if we let v equal x over y, so that says y is x times v. And then dy dx is x dv dx plus v. And that part never changes when we're doing this substitution for homogeneous equations. Once we know it's homogeneous, we do these same 3 steps all the time. And now we plug into the equation we're given. So that says x dv dx plus v is equal to v squared plus 2v. That's this equation. Here's my x dv dx, and here's the v squared plus 2v. All right, and now we try our best to solve it. Okay, so let's see. This will be x dv dx is going to be v squared plus 2v minus v, so this will be plus v. So rewriting that using good algebra, so I divide by v squared plus v, and I multiply by 1 over x dx on both sides, and I end up with this. That's separated, so I can integrate. This right-hand side is easy to integrate. You get ln absolute value of x. What about this left side? How do you integrate that? This is where you have to start to remember your calculus 2. So the way you integrate that is you think of that as the integral of dv over v times v plus 1. This is probably the easiest way to do that. And this one we can integrate. We said this is ln absolute value of x plus c. Okay. Now, how do you integrate this? Partial fractions. And yes, you do have to remember all of this. So 1 over v times v plus 1 is a over v plus b over v plus 1. And now you figure out what a and b is. So I multiply through by v times v plus 1. I get 1 is av plus 1 plus bv, which is av plus a plus bv. And now equating coefficients, that says a plus b times v plus a equals 1. Therefore, a plus b equals 0 and a equals 1. So a is equal to minus b. And since a is 1, that says that b is minus 1. Okay. So the integral of dv over v squared plus v is the integral of dv over v times v plus 1, which is by partial fractions, the integral of dv over v minus the integral of dv over v plus 1. Oops, sorry, wrote that where you couldn't see it. Okay. All right, and now this one's easy to integrate. This is ln absolute value of v. And how about this one? This is a simple substitution you think through. Let u be v plus 1, then du is dv. So this is the integral of du over u, which integrates to ln absolute value of u. But u was v plus 1. Okay, we don't need a plus c because we're going to put it back into this other side with this plus c, so we'll be okay. Technically, you need the plus c here, but later on, we're going to lump the constants together. Okay, so going back to this equation right here. So star becomes ln of v minus ln of v plus 1 is ln absolute value of x plus c. Okay, now notice, now we have to solve for v. So you really need all of your algebra skills too. So this is ln absolute value of v over v minus 1 is ln of x plus c. Okay, now take exponentials. You have to get the v out of there. So you e ln v over v minus 1 is e ln x plus c, which is e ln x times e to the c, which is just another arbitrary constant. So that says v over v minus 1 is c. E to the ln x is just x. Okay. So we are still not done. We have to solve for v. So this says that v is cx times v minus 1. So v is cxv minus cx. Which says that v times 1 minus cx is equal to minus cx. And so v is minus cx over 1 minus cx, and maybe that looks better to write it as cx over cx minus 1. Okay? But we are still not done because we started with y, we want to end with y. And y, v was equal to y over x. So this equals y over x. So in order to solve for y, I have to multiply through by x. So this is cx squared over cx minus 1. And there is our solution to that homogeneous problem. Okay. Okay, so that's it for how you do homogeneous equations. It's just that you can get into some pretty involved integrals in pretty much any of these problems that we're doing the entire time in this course. Okay, hope you enjoyed that. See you soon.